Okay, I just want to quickly go back over these examples of finding out whether a function is even, odd, or neither, because I feel like it was confusing the way that I showed you before, and I want to make sure that I'm doing it in a way that's the simplest and most straightforward way. So when you want to determine if a function is even or odd or neither, all you have to do is plug in negative x into the function. So f of negative x, and see what you get. So -2 times negative x to the fourth plus 5 times the absolute value of negative x. When you do that, you've got -2 times positive x to the fourth plus 5 times the absolute value of x, because the absolute value of x is the same as the absolute value of negative x. And so you can see that when you plug in negative x into this function, it doesn't change anything. It stays the same. So f of negative x is equal to f of x. And that tells me that the function is even. Okay, so you don't have to do anything else. You don't have to check if it's odd, because even functions are not odd. And yeah, so that's all you have to do. Okay, here you have another one. Same thing. You just plug in negative x into the function. So g of negative x is equal to 4 times negative x cubed minus negative x. And so this equals negative 4x cubed plus x. And you can see that that is exactly the opposite of the original function. And so since f of negative x is equal to the opposite of the original function, that means that it is odd. So that's what happens when the function is odd. Again, here's another one. We're going to plug in negative x. So h of negative x is equal to 2 times negative x squared plus negative x. And that is just 2x squared minus x. And you can see that that is not equal to h of x, and it's not equal to the opposite of h of x either. It's not h of x. It's not the same as it was to start with. And it's also not the opposite of h of x. Therefore, this function is neither even nor odd. Okay, I want to do this piecewise function again because I feel like I was just a little bit slow. We were all kind of falling asleep, I think, in class. Okay, so a piecewise function is a function that is defined in pieces. It has different behavior depending on where you are on the x-axis. So this function, f of x, has a value of negative x minus 1 whenever x is less than negative 1. So that would be all the places over here. It has a value of negative 3 when you are between negative 1 and 2. So in this area right here, it will always have a value of negative 3. And that includes negative 1, but not 2. And then when x is greater than or equal to 2, from this point up, that is going to look like this graph of the absolute value of x, except it's moved over 2 to the right. So to figure out the values right here, f of negative 3, you're going to look at where f is. If you just look at the graph, you can see that f of negative 3 is 2. But if you didn't have the graph, you could look here and you would see, okay, I'm using the x value of negative 3, so that occurs in this interval. So I'm going to put negative 3 into that function, and I'll have negative 3 minus 1 is 3 minus 1, which is 2. For f of negative 1, that x value occurs in this interval. And we know that in that interval, the function is always negative 3. And you can see on the graph that that's true. When you're at negative 1, the function is negative 3. And that's why you have a hole right here, because when x is negative 1, the function is not doing what we would expect it to do and just keep going down with this line. It has jumped down here and become negative 3. So we have to put a hole right there to show that there's a discontinuity in this function. It doesn't just continue to do what it's been doing. It completely changes. Okay, so then f of 2, that x value occurs in this interval where all the x values are greater than or equal to 2. And so for that value, if you look at the graph, you can see that it has a value, when x is 2, it has a value of 0. You could also figure that out just by putting 2 into the function that is defining the graph on the values x greater than or equal to 2. If you put 2 in there for x, you're going to get square root of 2 minus 2, which is the square root of 0, which is 0. For f of 6, you are going to want to look at this definition again, because in the area where x is greater than or equal to 2, which is where it is when x is 6, this is the behavior of the function. It's going to be the square root of x minus 2. So the square root of 6 minus 2 is the square root of 4, which is 2. So these are the values of this function based on what the function is doing on certain intervals. Okay? We want to graph the function defined by this piecewise function. F of x is equal to negative 3x for x less than 1, and negative 3 for x greater than or equal to 1. So what we have to do to graph this is we just have to look at the two intervals that we're talking about here. We're looking at the interval where x is less than 1. That means all these areas over here on the left of 1. And then the other interval we're looking at is x greater than or equal to 1. And that starts at 1 and goes up. So what does the graph look like on those intervals? So first of all, if we look at the values where x is greater than or equal to 1, we can see that that is always supposed to have a value of negative 3. So when x is greater than or equal to 1, we always have a value of negative 3 for our x. So that part of the graph is going to look like that horizontal line. And then when x is less than 1, we are going to have the function's going to look like negative 3x. And that means y equals negative 3x. That is a line. So that line looks like this. And I'm putting a hole there just because that particular part of the function doesn't have a value when x is 1, because x is less than 1 for that to be happening. But you don't need to put that because we have a dot there already, and these two pieces join. So you wouldn't put an empty circle there, because there is a value for x equals 1, and it is negative 3, and that is perfectly, actually that would be the same thing it would be if that line, negative 3, y equals negative 3x, were the function. So we don't need an empty circle because the two pieces join up right there. Now we have the function that says your function is going to be x plus 3. That means the line y equals x plus 3 for x less than negative 1. So when you're less than negative 1 here on the x-axis, any value you put in is going to have the value x plus 3. And then from negative 1 up to 2, that is going to have a value of x squared. So that is going to be the parabola x squared, y equals x squared. So we know that the line that's happening when x is less than negative 1 is the line x plus 3. And that would look like the line that has y-intercept 3 and slope 1. And since we can't draw the y-intercept because it's not having that kind of behavior after negative 1, we can just graph a couple of points. We know that if x could be equal to negative 1, you would put that into the equation, and you would have negative 1 plus 3, which is 2. So if the function for that part was equal to negative 1, it would go there. But it's not. So any value less than that would be definitely having that behavior of the line y equals x plus 3. So we can just put a few points on there, negative 2, 1, negative 3, 0, and then we can just draw that line. So that's what the function looks like when x is less than negative 1. It looks like the line x plus 3. When x is greater than, when it's between negative 1 and 2, not including 2, but including negative 1, we have these values. If x is negative 1, we have negative 1 squared, which is 1. And then we can put in these other values for all the area there between negative 1 and 2. Now, we did put a circle on the graph of y equals x plus 3 because these two do not join together. The parabola one has a value at negative 1, at x equals negative 1, and that is 1. The line part does not have a value at negative 1 because it's not including negative 1, and those two pieces do not join up. So this is going to look like a parabola from the parabola y equals x squared as you go from negative 1 on the x-axis up to 2. And I'm putting a circle there on 2 because we are not including that point, that value at 2, because as you can see, it says x less than 2. An important piecewise function is called the greatest integer function, or the floor function. It is defined by f of x is equal to the greatest integer less than or equal to x, which is what that double bracket means, where that symbol is, like I said, the greatest integer less than or equal to x. Sometimes when you see those double brackets, you can also see it written as int of x, which means integer function of x, or floor of x. So if we want to graph the greatest integer function, let's just look at a few points to see what's going on. When x is negative 1.7, and you put it in that little double bracket, if you put that value in the little double bracket, you're saying the greatest integer that is just less than negative 1.7. So the next integer down from negative 1.7, and that is going to be 2. Sorry, negative 2. So we would graph negative 1.7, negative 2. Next, you've got x equals negative 1, and since that already is an integer, the greatest integer less than or equal to negative 1 is just negative 1. Now you're at negative 0.6 for x. The greatest integer that is less than or equal to negative 0.6 is going to be the next integer down, which is negative 1. Sorry, I forgot to graph negative 1, negative 1. So negative 1. So negative 0.6, negative 1 is also on this graph. Then you have x equals 0, and the greatest integer less than or equal to 0 is just 0. So 0, 0 is on this graph. Then you have 0.4 for x. The greatest integer less than or equal to 0.4 is 0. So that point, 0.40, is also on this graph. If x is 1, the greatest integer less than or equal to 1 is just 1. So 1, 1 is on the graph. If x is 1.8, the greatest integer less than or equal to 1.8 is just 1. So 1.81 is on the graph. If x is 2, the greatest integer less than or equal to 2 is just 2. And then if x is, well, we have to graph that. 2, 2 is on the graph. And then if x is 2.5, the greatest integer less than or equal to 2.5 is still just 2. So the point 2.5, 2 is going to be on the graph. So you can see how this graph looks. It just looks like several floors or steps. So this is what it looks like. When x is negative 2, the function is negative 2 all the way up until you get to negative 1, and then it jumps up to negative 1. So it doesn't have a value for negative 1 down there at negative 2. It pops up to negative 1 then, and it stays the same until you get to 0, and then it pops up to 0. And then it stays the same until you get to 1, and then it pops up to 1 on the y-axis. Once you get to 1 on the x-axis, put 1 into the greatest integer function, you get 1. And you stay at 1 all the way until you get to 2 on the x-axis, because then the greatest integer less than or equal to 2 is 2. So you have to pop up to that next y value. So that's the greatest integer function, or the floor function. Okay, so example 8. A salesperson makes a monthly salary of $3,000 along with 5% commission on sales over $20,000 for the month. So write a piecewise function to represent the salesperson's monthly income, I of x, in dollars, for x dollars in sales. So there are two situations. You accomplish $20,000 or less in sales in a month, and we'll call that amount x. Whatever amount you sell, we'll call that amount x dollars in sales for you. And that is less, it's less than or equal to 20,000. So you don't sell over $20,000 worth of merchandise. If that happens, if your X dollars in sales is less than or equal to 20,000, you don't get a bonus, you just get 3,000 total. Or you could accomplish over $20,000 in sales in a month, then you're going to get to add 5% commission. This means you get to keep 5% of the money from the sales you make over that $20,000. So if X is equal to the amount used in sales, that is the value of the merchandise you sold, if you sell more than 20,000 in sales, you're going to have to figure out how much more than 20,000 you sold, because that's the amount you'll get that 5% bonus on. So X minus 20,000 is going to be the amount in sales that you made over 20,000. So we're looking at these two scenarios. Like I said, if you make over 20,000 in sales in a month, you'll be paid 3,000 plus 5% of whatever you sold over 20,000, which is X minus 20,000. And so this is the situation. We have a piecewise function here. I of X, that is your income for the month. There's two situations. If you sell from anywhere from 0 up to $20,000 worth of merchandise, that's the first scenario, you will get $3,000. That's it. The second situation is if you sell over 20,000, so for X greater than 20,000, you're going to get your $3,000 plus 5% of X minus 20,000. That is the amount you sold over 20,000. So that's what that piecewise function looks like. Okay, now we're going to look at intervals of increasing and decreasing and constant behavior. When you look at a function like this, f is increasing on I, on whatever interval you're on the x-axis, if f of x sub 1 is less than f of x sub 2 for all x sub 1 less than x sub 2 on I. I know that sounds complicated, but it just means that as x gets bigger, y gets bigger. That's when you know the function is increasing. That's an increasing function. It just means it's going up. All right. A decreasing function is when for each x, as x gets bigger, y is now getting smaller. So a function is decreasing on I if f of x sub 1 is greater than f of x sub 2 for all x sub 1 less than x sub 2. So as x gets bigger and bigger, the function is going down. F of x is getting smaller. So that is a decreasing function. It just means that it's going down. A constant function stays the same. The value of the function stays the same on that interval. So f is a constant on I if f of x sub 1 equals f of x sub 2 for all x sub 1 and x sub 2 on I. Okay, so we're going to use interval notation to write the intervals over which this function is increasing, decreasing, and constant. All right, so for increasing, you can see if you start over here on the left, it's going down, so that's not increasing. Then between -1 and 2, it's constant. From 2 to 3, the function is increasing. So that's really the only place that the function is increasing. And so we would write from 2 to 3 for increasing. And we would use parentheses. We would not use square brackets because at a particular spot, the function's not doing anything. It's not increasing or decreasing. So you wouldn't include 2 and you wouldn't include 3. Okay, where's the function decreasing? Well, you start over here at -4 on your x-axis, and you can see that it's up there at 4, and then it begins to go down. The y value of the function begins to go down. And it keeps going down until you get to -1 on the x-axis. And so we would say that the function is decreasing from -4 to -1. And again, we're not going to use square brackets for increasing or decreasing. And then there's another place where the function is also decreasing. It's decreasing as you go from 3 to infinity on the x-axis. So we would say union 3 to infinity. The function is constant from -1 up to 2 on your x-axis. And here we will use square brackets because constant just means it stays the same. And so here we would have -1 up to 2. Okay, relative maxima and minima. A relative maximum of a function is a place where f of a is greater than or equal to f of x for all x near a. So it's a little bit of a informal definition, but basically what it's saying is that if f of a is a relative maximum of f, it just means that f of a is the greatest function value relative to other points nearby. All right, so it's like a top of a hill or the bottom of a valley. That's what a relative maximum or minimum is. So here you can see that f of a, this point right here, is higher than the other function values around it. It has greater function value than these other x values around it. You can see that f of a is a relative minimum of f. It just means that f of a is the smallest function value relative to other points nearby. So here you've got Well, this should really be f of b is relative minimum, means that f of b is the smallest function value relative to other points nearby. So here you can see this point, b, f of b, is a minimum. It's the lowest point in that area. And so b, f of b is, we would call f of b a relative minimum. So the way we would say this, we would say there is a relative minimum of f of b at x equals b. So for the graph of y equals g of x shown, determine the location and the value of any relative maxima and minima. So if you look down here at the bottom, you can see that there's a low point at -1, -5. That is lower than any of the other function values near that. The location of that minimum, location, we would say, is -1. That's where you are on the x-axis. We would say the value of it is -5. So we would say a relative minimum of -5 at x equals -1. So the location is -1, the value is -5. Then we look over here, we see another point that is higher or lower than the points around it. That one is higher than the points around it. We would call it a maximum. So here we have a relative maximum of 1. So f of 2 is 1 at x equals 2. So there's a relative maximum of 1 at x equals 2. So the location is where we are on the x-axis, and the value of that maximum is 1. Then you can see we have another one. This is a minimum. So we have a relative minimum of -2 at x equals 4. So the location is 4 and the value is -2.